Hello, my name is John Bormeder, and I was until the last minute not quite sure if I can do this presentation and if I will have enough new things to share with you. And this project was part of my Wolfram Summer School project of this year. And I wrote some code on them, and as sometimes happens, one thinks that one will have a lot of time to develop it further, and that was my intention. But that amount of time was not available to me, and so yesterday morning I thought, okay, like, can I really use my framework and can I add some more games to it? And well, here I am. So it did work. I managed to add some games. So if you're familiar with that project, there will be something new as well. And then if you're not, then at least that, that should provide a first verification of the viability of this framework, or so I hope. I cannot quite see the chat and my screen at the same time, so I just hope I will, once in a while I will check back here to see if there are any questions. Okay, so combinatorial games are we'll define combinatorial games without doing a formal, technical, mathematically rigorous definition. All we can say is that combinatorial games involve two players who move sequentially, so starting with player one and player two and player one. There's perfect information, so everybody observes everything concerning what their opponent do, as well as the consequences of their own actions. Nothing is hidden, everything is open to view. And there are most combinatorial games come in two flavors, what is called normal play and misère play. So under normal play, the first player without any available moves loses and their opponent wins. And in misère play, it's exactly the opposite. So the first player without moves wins. And if you want to think of combinatorial games, there are examples aplenty. So I actually found this today, that Connect4 is an entity, and you can look up its definition. And I think you probably remember this from your childhood. You have to drop tokens from top to bottom, and the goal is to achieve 4 tokens in a sequence. Some combinatorial games may be played with paper and pencil, and so I also found the definitions of dots and boxes in there, although there was no image associated. And they also involve some, or like this set of combinatorial games includes some commercially successful ones released in the last years. For example, Corridor is one of them. Players have to either move their pawns on a grid or place or replace walls to block the other's movement. And so what emerges is sort of a maze-like structure that players have to navigate. Go is an ancient combinatorial game. It respects all of the requirements of the definition, except perhaps you have to adjust the winning condition, because in Go it's a point scoring game, but you can rephrase it to become a combinatorial game. And actually the first game that we have evidence of, although this is disputed like much in archaeology and history, is a combinatorial game. It's called Mancala, and you may be familiar again with it from your childhood. And so this is an example of a recent archaeological dig, if I remember correctly, from Ethiopia, where they found what clearly looks like Mancala-like structures, and they are hypothesizing that this is some sort of a gaming parlor that was in this particular area. And Connected to, or while we're at it, you can look up Bob Nutber's Wolfram Tech Talk from last year on the multi-way analysis of Mancala. So counterexamples to combinatorial games are games that have turn-taking, have perfect information, but involve more than 2 players. And so Chinese checkers is one of the examples. And again, we find the definition in the form of an entity. There are non-perfect information games, whether they are played by 2 or more players, like poker. And so there's some things that are hidden from the view of the others, and so they wouldn't fit into this category. Or games where a draw is possible, like chess. So chess otherwise looks very fitting to our intuition of what might be here, but it's technically not a combinatorial game. But of course, while these are all counterexamples, some are closer to combinatorial games than others, and combinatorial game theoretic analysis reveals more about chess, for instance, or can get, is much more helpful for understanding chess than, for example, for analyzing poker. I'm going to quickly check if there are any questions. If I could share the notebook. I'm happy to do this after my talk was finished. I was editing it to the last second, but if that is sufficient, I'm happy to do that later. Is that okay? Okay, that's what I can offer. Okay, no more questions. So let's proceed to why we are doing this. And the reason why I was aiming for a comprehensive framework for combinatorial games is that, first of all, it's very close to the spirit of some of the projects that have been going on in recent years at Wolfram. And so, multi-way analysis and multi-way graphs are very, or are the tools required for analyzing combinatorial games, even though they're principally used for things like the physics projects and such. And if you are here listening to this talk, it is highly likely that you have seen the puzzles and games as multi-computational systems blog post by Stephen and Brad. And so I think there's enough justification there as to why these structures reveal some similarity and why it might be interesting to deal with them beyond the simple reasons that they are just plain fun and maybe intrinsically interesting if you play these sort of games relatively often. Now, as we were or if you look at how this sort of analysis is done in that blog post, and also on some other posts on combinatorial games on the community side, it is very ad hoc, and so many of the functions are rewritten over and over again, which is a waste of resources and never a good coding practice in general. And so in my previous summer school project, I was trying to implement I've implemented Hackenbush as a combinatorial game, but I felt like much of the code that I'm using is not very specific to Hackenbush, but can be and should be used over and over again for other games as well. And so this summer I was trying to figure out how to create a framework to do just that and save us some time and sort of to have a unified framework to deal with these things. And the approach that I took is to use object-oriented programming in the Wolfram language and to use entities. Now, both of those choices may be contentious. And so why object-oriented programming, and what do we need for that? And so it turns out this is a long requested, debated. It's a very murky area of whether and to what extent the Wolfram language is good for object-oriented programming, and whether we need object-oriented programming at all, and how to do it. And so what works for me is a packlet developed by Nick Merzin, and yeah, I don't know how to share my browser screen at the moment, but you can look it up. And this is relatively new, and in July this was not part of Wolfram core, and now it seems that there is some sort of class functionality, as you can see here. If I should, or normally one gets a warning that some of the functions are overwritten. Anyway, the current version of my framework requires the packlet form of the class. And the other choice was for entities. And so I felt that information about these combinatorial games should come in sort of a packaged way, so that you can access them very easily, and also that users, when, for example, they're trying to play one of these games, like they're trying to play tic-tac-toe, they might not care about the details of the implementations of the rules, and can just trust that this is done in a way that that works. And so I'm going to show you what or how it looks at the moment. I try to make this framework very modular. So each class definition is in a different file, and currently, so this is why this notebook, while I will share this notebook, it is not entirely self-contained. As you look to these lines, it looks up some files on my respective folder. And I'm sorry, let me remove this. And how this looks at the moment is that game entity game is an entity, and so is a combinatorial game, and so is a specific game like tic-tac-toe. Okay, and these form a hierarchical structure. So so the superclass of tic-tac-toe games is MNK games, and MNK games are combinatorial games, and combinatorial games are just games. So I was also trying to come up with a framework that will work later on if we move beyond two-player games with perfect information. And so what I implemented in the summer school was tic-tac-toe, and now I've added two simple new games, Chaos and Nim. But the fact that I could do this, with very little time, seems to indicate that this is feasible. And I want to show you there's yes, that I think that is the link that Brett just posted. So I'm just checking if that is indeed correct regarding the class package, and that is indeed correct. Yes. And so each of these classes have their own files, and I just want to show you how each file looks. And this is the most general one, and here are the functionalities that so far I'm thinking all of the games that we have would require and use. So we have we can ask for the current state. We can change the position of a game. We can ask for whether the current position or any position that we hand to this function is an end state, and who is the winner within that. For the current position or any position that we pass to this function, we can generate the set of possible moves. We can also see the next possible states. So basically applying all possible moves and generating a list from them. We can execute moves, so changing the internal state. We should be able to draw states and generate game graphs. And so now the details are not very important, and these functions mostly refer to other functions, and that these are the things that we don't want to implement over and over again. And so let's look at, for example, chaos that, as I said, I implemented very, very recently. Like what do we have to define in order to have that game ready? So we need to specify its name, its superclass, an alternative name, a description, and a link, so that this can be relatively easily filled in. And the magic sort of happens inside of this run type definition entry. And what we need to define for each game that we're implementing is what is crucial is this function endStateQ_winner. So this returns an association on whether a certain state is the end state, and if so, who the winner is, the set of possible moves, and how the next state is generated for any of the possible moves. There's a drawing functionality, and this legal state Q, this is not strictly necessary, but it helps for debugging, because it ascertains that the format of a certain state that we pass on to this function is valid, and so that can be helpful. And so for CHAOS, let me explain the rules of CHAOS, and then we can look at the implementation. The game consists of having a row of bowling pins, and players can take turns to knock either one of the pins or two of the adjacent pins. So you might imagine like a row of pins starting out. Maybe we started out here with something like 8 pins, and the first 2 moves involved removing pin number 3 and pin number 7. And the next move by the first player could involve dropping pins, these pins in the middle, these 2 pins in the middle. And so what we need here is a function determining whether we're in an end state, and we're in an end state. I forgot to mention it's a normal play, so the player who has no more pins to bowl out loses. So we're in an end state simply if if there are no remaining pins, and in this case, the opponent of the current player, so the player whose turn it is to move, is the winner, and otherwise we're not in an end state. And we would also need a function generating the set of possible moves, and we'll see how that works in a moment, but it's basically this. And we also need to generate the next state for each of those moves, and basically we're just removing the pins and creating lists as necessary. So let's see how this works. I hope I registered everything correctly, but we will create a new instance of the CHAOS game. Let me just quickly look, I have about 10 minutes left, representing exactly this state that we have above. And as you can see, this is just a CHAOS game object, and its initial state, we adopt the standardization that we always order the number of pins in decreasing order, and the player to move is player number 1. And we can save the current state, and you can see later if we save the current state and then we can update that internally, that doesn't change. Moreover, we can also copy games, so if we want to preserve the game in any specific position, that is very easy with this approach as well. And this is more interesting. This just determines whether we're in an end state, and well, since it's not an end state, we don't have a winner. Let's look at the possible moves. So this involves this is basically a pair or each possible move is a pair representing which sequence of continuous pins we can knock down, and which ones to knock down. So in this state where we have 4 pins in row in the first sequence, we can knock down just the first one, just the second one, just the third one, just the fourth one, or adjacent ones as represented here. Okay, and so the current state is just this. We can check what would be the next state after executing a sequence of moves. So for example, if we knock down from the first pile, the middle 2 ones, and what then happens is we will get 3 sequences of 1s and 1 sequence of 2, which is exactly what we get here. And the next player to move is the opponent. We can here notice that with next state moves we did not actually update the internal position. It just reports, or gives back what the next state would be. Here we can get sequence of all the possible next states for from the current position. So you can see you can knock down 1, or you can knock down some middle ones like we did before. Make moves actually executes well, this should be 1, but okay. Oh yes, we knocked down 2 pins in sequence, so we ended up with this state. We can draw it, which is just currently text, or like writing a list in text form, and then we can generate the game graph. So for a depth of 2, so like all the possible states we can achieve from this state by updating. Well, in this case, it's not very interesting. Let me actually rewrite G and see how it looks like for this more complicated situation. Okay, it's not very pretty, so visualization needs improvement, but it works. NIM is a similar game, and yeah, I don't want to go into its cultural representations, although that is worth a lecture of its own. But I think NIM is familiar to all of the attendees here. You have piles of objects, and each player on their turn can remove from one pile as many as they want. And so now we can create a NIM game, and we can do, for example, the same sort of operations as we did here. So, for example, this is not an end state. We can check what the possible moves are. In this case, this is a pair indicating how many elements to remove from the first or the second pile. Okay, we can also generate the game graph for this. And yeah, that also doesn't look very pretty, but yeah, graphics is kind of the hardest element of this. And let me reflect on that in a moment. So what are the next steps? So obviously we can add more games. So our aim is to integrate it with existing functionality from the Wolfram function repository. There is a little known function that called directed cyclic evaluate, which is essentially a minimax algorithm, or I'm assuming maybe it is much more frequently used than I'm aware. Also, Brad Klee, who was my mentor for the summer school project, and Andrea Lee, who is a very young contributor to the repository, they implemented alpha beta search. I always told them, and I think that these integrations are rather easy, but I didn't do it yet. More functionality that could be interesting is to have functions for the history of games, and again, this would work very broadly. So we would, basically for all of the games that we encode, it would work in the same way. More game-specific functionalities would be to account for positional symmetries. So just as like we were sorting the sequences of pins and KLs, that can reduce the apparent state space, and this is useful for generating game graphs. And destructors should be quite easy. I've spent the most time trying to come up with nice visualizations, and for the summer school that involved only tic-tac-toe, and even that took a considerable amount of time, and so I'm not quite sure how to come up with best visuals. But one thing I realized is that the generation of the game graph should be separated from its visualization, because often why generating the game graph takes a long time is because of the graphics. Other more mid or long-term goals would be to create data structures for searching. I know that some people were working on Monte Carlo tree search. I was looking for these in the repository, but they did not appear yet. So integration with Monte Carlo tree search again should be, or I expect it to be relatively easy. There should be more heuristic game-specific search algorithms, and since most of these games have, like, not libraries, but at least several monographs written on them, there is much to be done there. Also implementing some sort of neural networks, finding good strategies for these games. I don't know how generally this can be done, but it can be done. Okay. Thank you to a lot of people, especially Brad, who bore with me for 2 summers already, and Andrea Lee for her inspiration, and Nick and Christopher helped me a lot, specifically with understanding how to use object orientation, and of course to Stephen for inspiring this whole thing by bringing up the idea of the analogy of puzzles and games as multi-computational systems and their similarity to certain physical structures. Thank you very much, and I will now try to look at your questions in the remaining fantastic 3 minutes that I have. Directed acyclic evaluate is planned to be promoted to systems, so that's good to know, and that also implies a lot more people are using it than I'm aware. And that it requires a rewrite. I should note that I commend that direction, because at least as a naive user, it took me a significant amount of time to understand how it works and what it does. And every time I understand it, there is still this horror of returning to it and understanding it deeply again. So maybe the examples that are provided within that context. That's not meant as criticism, but I think we can make it more user-friendly. Okay, thank you for your attention and your interest. Oh, so many questions. I want to see the Q&A. So I'll try to quickly respond. Oh yeah, Packlet. I wanted to turn this into a Packlet, but I need time to figure out how to do that. And maybe if I go to the summer school again, that would be a great time to do it. But yeah, if there's interest, yes, certainly. Is this applicable only to tic-tac-toe, or can we apply to Sudoku, chess, Chinese checkers, Go? So Sudoku is not a combinatorial game. It's like a single player decision problem. And I think there's a Sudoku solver. In fact, I went to a workshop on Sudoku solving. And also I think like sort of brute searching for Sudoku solutions is difficult. Chess, I think, should not be far off. with Chinese checkers, with multiplayer games in general, and that is why if yeah, I can make a small detour. So I've spoken to the people in London who developed AlphaZero for chess and AlphaGo. What is it called? AlphaGo. So recently they have been working on multiplayer games like Settlers of Catan. If you know anything about Settlers of Catan, or like you know about them, about it, your impression might be that that's a simpler game than either chess or Go, and that's not the case because of the strategic coalitional aspect. And so everything where coalition building is possible requires some sort of negotiation and bargaining, and that's intrinsically more difficult. So not Chinese checkers, but Go, I don't see why not. And things like chess and Go would especially be amenable to like more specific heuristics than the sort of backward induction solving, or AlphaZero, alpha beta pruning. That should work well here. What is the relation between this and the new matrix and tree game functionality in 14.2? Nothing. I'm myself not, I should have amended this whole talk by stating or clarifying that I'm not an algorithmic a game theoretician. I'm actually much more a traditional game theorist, and so I know about those functionalities. And this is a hobby project, but it's entirely independent of what is done for 14.2. The notation with strings having brackets attached. Yeah, that's specific to this like object-oriented approach, but maybe there's a better way to do it. I don't know. Go can be rephrased into a combinatorial game. Do you mean by extending the definition? I have to think about the question. I don't want to run ahead. What is the role of search algorithms in combinatorial games? Well, they provide optimal strategies, or optimal play paths for both players. Yeah, that's as short of an answer as I can give you now. Thank you for the attention. This is my first tech talk ever. It was significantly more different than the traditional academic talks that I'm used to giving. And so thank you for bearing with me. See you around, I guess.